Everyone. Welcome back. So we're having this discussion about the various types of geothermal power plant cycles, and we covered all of them from the dry steam to flash to binary geothermal power plant cycles. And what we want to talk today is about the combined flash and binary geothermal power plant, which is also something that's possible and makes sense in some cases. So what are we looking at? Well, what we have is initially a flash kind of a cycle where you take the hot water, water from the geothermal resource, you send it through a flash chamber to flash or reduce the pressure in an isothermal in an isenthalpic manner to get a two-phase mixture, a saturated liquid vapor mixture at state two, and then we send it through a separator to separate the liquid and the vapor part. The saturated liquid part, we send it down here. The vapor, of course, is at the top because of its lower density. We extract it and we send it to a turbine, just like we would do in a typical flash chamber, or sorry, a typical flash geothermal power cycle. Now, what is different here is that what we are doing with this saturated liquid water, normally for a single flash cycle, you can simply re-inject it back onto the ground. Another option could be to send it to another flash chamber and then separate it and operate a dual flash a geothermal power plant. Now, this option here is slightly different. Here, what we are doing is we are taking this hot water and we are sending through heat exchangers so as to power or to to transfer heat to this another cycle, which is uh, the binary cycle, essentially using another working fluid, which, as we said before, is are typically refrigerants. So the difference in this combined flash slash binary geothermal power plant is essentially what we do with the saturated liquid that comes out from the separator, right? So here we are sending it through a heat exchanger to heat up or to transfer heat to this fluid going through the binary cycle. And as we discussed before, the working fluid of the binary cycle has a much lower boiling point. So as the water transfers heat, this allows the working fluid of the binary cycle to get vaporized. So it gets converted from liquid to vapor, superheated vapor usually, and then it expands again in this binary turbine. So essentially what we're going to get now is work output from two turbines, the steam turbine and the binary cycle turbine. Both are completely different working fluids. And basically, the purpose of this is that we have been able to better utilize the geothermal resource that we had, right? So in terms of the network output divided by the energy input, we're getting the energy output from two turbines, the steam turbine and the binary turbine, as shown here in this formula, right? So these are two different work outputs minus the work input for the pump, usually for this binary cycle. Now, the work input for the pump can also can be negligible in most cases. You can set it to zero. It's really small in most cases as a and compared to the work output from the turbine. But we have to sort of take the work input required for operating the fan. So this and where's the fan? Well, that's the fan that's used for cooling the binary working fluid. We said the condenser for the binary working fluid is air cooled, and so the fan work input can be reasonably large, about 20 to 50%, depending on the weather conditions. So yes, this is another cycle that we can have, and it's again which cycle that do you use? It depends on the geothermal resource you have, depends on what works out economically well. Okay, now moving on, the last way you can sort of still make use of the energy from a geothermal resource is to, well, do cogeneration, meaning you generate electrical energy plus some thermal energy, right? And here, this is just going to give us a better utilization for the geothermal resource that we have. And the idea is that once you have extracted the thermal energy for producing electricity through a turbine, before re-injecting the geothermal resource or the geothermal water back into the ground, you would want to extract a little bit more heat if it's available, right? And we will solve a couple of problems where we get to know what are the temperature of the geothermal water that goes back. And in some cases, it makes a lot more sense to sort of extract more heat from it rather than dumping it back into the ground. So in all such cases where you can provide um, electrical energy in a typical geothermal power cycle, plus some thermal energy by making use of the geothermal brine that's coming out from the turbine at the exit of the turbine of one of these power cycles, well, we'll just end up extracting much more overall energy from the same resource. So that's something that can bring down the cost by increasing the revenues, and also it's essentially a better use of the resource that we have. Now, ultimately, when we talk about different energy conversion sources, the bottom line is how much money does it cost to operate such an energy conversion system over its entire life cycle. And the levelized cost of electricity gives us a very good estimate uh, of the lifetime cost of any different different energy conversion sources. So this is a picture. This is a plot of the uh, dollars per kilowatt hour for different technologies. So this is from 2016, right? And the size of the bubbles that you see here indicates the capacity of the power plant built, right? So the bigger uh, bubbles refer to much bigger capacity. So the biggest bubble, for example, that you see here corresponds to capacities greater than 300 megawatt, which is reasonably large. And this again is from IRENA renewables database, as mentioned here. So what are we looking at? So we're comparing sort of the fossil fuel cost versus geothermal here, and then we're comparing it with the hydro, solar PV, concentrated solar, offshore wind, onshore wind, and so on and so forth. Now, obviously, one of the major changes that has happened in the last 10 years, if you look from 2010 to 2017, what this plot is showing, is a huge drop in huge drop in the prices for solar PV, and we see a similar drop for concentrated solar, not so much, but still a drop. And again, for wind, both offshore and onshore, and this reduction in prices has enabled us to sort of increase the penetration of renewables into the grid, and has is behind the revolution that we're sort of seeing now in terms of the power generation. These are reasonably good sources that can allow us to generate power or electricity with relatively low carbon footprint, right? And so this main change has allowed us to integrate them quite well into our grid without exorbitant increases in the cost of electricity, of course. Now, the other thing that you want to see is what are the uh, how does geothermal compare to other energy conversion methods? So if geothermal compares well, that's when it makes sense to look at any of these power cycles. And again, these are figures. These numbers for the cost will change from geography to geography, location to location, but these are more or less indicative of what to expect. Now, when we look at the geothermal power plant, so this is what we have for geothermal here, and the geothermal cost per kilowatt hour in US dollars has sort of increased from 5 cents per kilowatt hour to 7 cents per kilowatt hour as we have expanded more and as we have increased the amount of geothermal power capacity that we are building. So here we had most of the earlier ones that we had were relatively from good resources. So high temperature water or usually dry steam. So their costs were very low. Now, as we start to extract energy from other, let's say, geothermal resources where we just have maybe hot water, not dry steam, then the costs tend to go a little bit up. But the overall trend that you can see from 2010 to 2017 is an increase in the amount of geothermal electricity being produced, right, from geothermal resources. And there has been a slight increase in cost, of course, but you can see still in the range for fossil fuel. So fossil fuel range is basically the shaded region, and it's very much within the range, right? And the one on the left is for biomass. So biomass is again very much within the fossil fuel range. Geothermal is also within the range, as is hydro for most part. So basically, if you compare this with other renewable energy sources, well, geothermal is already in a relatively comfortable price range. So it makes sense to sort of figure out how can we extract more power using geothermal resource, how we can sort of use it to meet more of our energy needs. Remember, it'll not be able to meet all of our energy needs. It will at best probably contribute to 10%, right, of a given country's energy needs. but it's still a lot as a very good way of providing low carbon electricity. So it's something that's very useful simply because it is consistent, it is reliable, it is not intermittent, and it's renewable. So it's a very good option to have. Now let's solve a couple of problems to understand how what are the typical numbers associated with the geothermal resource in terms of efficiencies, in terms of temperatures, so on and so forth. Okay, so let's see what we have here. So first one is the analysis of a single flash geothermal power plant. Okay, so this is the first example we will look at. So here we are told that geothermal liquid water at 200 degrees Celsius, right? It's extracted from a geothermal well at a rate of 100 kilogram per second. So we know the temperature and we know the rate at which it's extracted. Now this water is flashed to a pressure of 500 kilopascal. This is water. It's high pressure water, presumably, simply because it is still in liquid state at 200 degrees Celsius, so the temperature, so the pressure is of course much higher than atmospheric pressure. Now, what we do is we flash it to a lower pressure, which is 500 kilopascal, in a flash chamber. And when you flash something, what's going to happen is that we will get a mixture, right, of liquid and vapor, and then we separate it as we discussed before. Now, the other option we have here, the other information we have here is that the condenser of the cycle, as we see here, this part right here. Now this condenser is maintained at a pressure of 10 kilopascal. So we have the pressure for the flash chamber, we have the pressure for the condenser, and the isentropic efficiency for the turbine is given 83%, right? That's for the steam turbine. Now we have to do a couple of things, find out the power output efficiency and so on and so forth. But to do any of that, first what we will need is the properties, right? So let's go ahead and figure out what are the thermodynamic relevant thermodynamic properties. Let's start with state one, right? So for state one, we know the temperature is 200 degrees Celsius and we know it's in liquid state. Now, from our knowledge of basic thermodynamics, we know that if we're dealing with a compressed liquid, right, then we can approximate its properties by knowing its temperature. So if you know the temperature, then you can say the enthalpy of compressed liquid with the state one here is approximately equal to the enthalpy of saturated liquid at the same temperature, right? At 200 degrees Celsius. So we know the temperature and that's more than enough, right? So using this temperature, we can get the enthalpy of saturated liquid, which comes out to be 852.26 kilojoule per kilogram. And this enthalpy would be very similar to the enthalpy for the actual geothermal water that we're extracting. Okay, so at this condition, the pressure is 1554.9 kilopascal. Now, this is the minimum pressure that you can expect to have at 200 degrees Celsius, right? So the geothermal water that we're extracting could be at this pressure or at higher pressure, right? It's compressed liquid. So this pressure or higher pressure, but pressure does not really play much of a role in terms of defining the enthalpy and other properties for other thermodynamic properties as far as compressed liquid state is concerned. So for now, state one, we have everything that's known, right? We know the temperature, we can find out the enthalpy, and that's an important part. Now, we know that the process from 1 to 2, the flashing process is isenthalpic, meaning it's constant enthalpy. So H1 should be equal to H2, right? So we know for state 2, we know the enthalpy and we know the pressure because it's given in the question that it's flashed to a pressure of 500 kilopascal. So initially it was at a higher pressure, 1554.9 or higher, and it was flashed to a lower pressure. And so now we have two properties. We have pressure and enthalpy. Using these two properties, we can find out the state of the mixture that we have at state 2, right? So the at state 2, the temperature is 151.83 degrees Celsius. So this is essentially the saturation temperature at 500 kilopascal. So this is Tsat at 500 kilopascal. Okay. The at state 2, we have a mixture of saturated liquid and vapor. As we said, the vapor is what ends up going in the steam turbine. The liquid is what we send to the condenser. We reinject it back into the well. So when we look at H6, H6 is simply HF at 500 kilopascal, which is 640.09. And H3 is enthalpy of saturated vapor at that condition. So it's 274.8.1. So now we have quite a few properties. We need some more though. The next property that we would want to find out is basically H4 as well, right? So now in terms of the another part that's going to be useful is to find out how much do we have in terms of the quality, right? In the sense that, okay, we have a mixture of liquid and vapor at state two, but how much of it is liquid and how much of that is vapor? You can find out by basically using the formula for enthalpy of a saturated mixture. So H2 is simply HF plus quality at state two, X2 times Hg minus Hf. Okay, so we have Hf given here at 640.09. Hg is given here 2748.1 at 500 kilopascal. And H2 is something that we know. It's 852.26. So by using all of this information, we can simply calculate X2 as H2 minus Hf by Hg minus Hf, or what's commonly called as Hfg in the tables. And by doing the math, we can calculate the quality at state 2 to be 0.1006, right? Essentially, only 10% of the initial fluid is converted to vapor, right? The rest is all liquid. Okay, so now in terms of properties for state three, we have information for state three, and we said, okay, state three is saturated vapor, and this is the enthalpy, and this would be entropy, right? This would be the entropy. This is again simply S Sg at 500 kilopascal. Now, for finding out the properties at state four, well, we will have to do that in a two-step process as we normally do. So first thing is we assume isentropic expansion. We assume that the expansion from 3 to 4 is isentropic, which means that we say, okay, S4 is equal to S3. Now, we also know what is the pressure at state 4 because that's the pressure of the condenser. You know that P4 is 10 kilopascal. So using those two information, what we can do is we can find out the thermodynamic properties at state four, right? But remember, those are the ideal properties because we sort of assume the expansion to be isentropic, which is not the case. So for finding the isentropic the enthalpy for the isentropic process, take pressure P4 and S4 is equal to S3, right? And S3 is what we found here. Using this, we find H4S to be 2160.2 kilojoule per kilogram. Now, in reality, the enthalpy is going to be higher than that. So we do that by making use of the isentropic efficiency formula and the isentropic efficiency for the turbine given in the problem. So here we'll just make use of the isentropic efficiency formula for the turbine. This is H3 already known. H4 is what we want to find out. H4S is what we just found out by assuming isentropic process, and the isentropic efficiency is already given, right? So um, H4 is what we need to find. H4S we already calculated. H3 is known. So the only unknown is H4, and when you solve for it, you get 2260.1 kilojoule per kilogram. As expected, H4 should be greater than H4S. Okay, so now we have almost all the properties that we would be interested in. So now let's go ahead and look at what we need to solve here. So the first part is what is the mass flow rate of the water vapor at the turbine inlet? So essentially we're asking what is m dot 3, right? Because we know that is the only part that goes on expands in the turbine. So well, m dot 3 is simply uh, it depends on what is the quality that we have at state 2, right? So quality is something that we determined previously, and once you have the quality, then the quality is simply a function of how much the mass of the vapor divided by the mass of the total mixture, right? And the mass of the total mixture is exactly equal to the mass of the uh, water that we're extracting from the geothermal well, m dot 1. So m dot 1 is equal to m dot 2, right? And at this point, it gets separated into m dot 6 and m dot 3. M dot 3 is simply quality times m dot 1, or 10% of m dot 1. So what is m dot 1? Well, m dot 1 was 100 kilogram per second. So 10% of that is 10.06 kilogram per second, right? Not exactly 10%, 10.06%. So this is the mass flow rate of the steam that we get from this geothermal resource, right? So it's very interesting that out of the 100 kilogram of per second of geothermal water that we're extracting, only 10 0.06 kilogram per second is sort of expanding in the turbine and giving us the power output. The rest is just being reinjected back into the well, right? So when you look at m.6, which is the mass flow rate of the hot water, remember this is still very hot, right? So the temperature at state 2 was about 150, 151 something degrees Celsius. So it's not really cold. It's reasonably hot, although not very hot. So it's difficult to maybe use it for power generation in another flash cycle, but it may make sense to use it in maybe a binary cycle, or it could also make sense to use it for just heating purposes. So reasonably hot water and at really high flow rates, right? So the mass flow rate of water that we have here, m.6, it's what's remaining. So it's 89.94 kilogram per second, right? So it's still hot, it's still a lot of water to be used. So essentially, about 90% of the water that we extracted, we are just re-injecting it back into the well, and it's going back at 151.8 degrees Celsius. So hot water, very high flow rate, all the way going back. So this is an opportunity for us to sort of make use of it for different purposes. We don't do that in a single flash, maybe because, well, the economics have to work out if we want to do that. Okay, so for now, let's just keep in mind that sometimes the water that you reinject into the well could be reasonably hot, right? As we see here. Now, the second part is to determine the power output from the turbine and the thermal efficiency of the plant. The power output from the turbine is very simple. It's simply m.3 times H3 minus H4, right? We have H3, we calculated H4 already, so it's just a matter of plugging in the numbers. So when you do so, we get the work output. It's about 4.9 megawatt. Reasonably large, not so small, right? Enough to power a few homes, right? So in terms of thermal efficiency, well, thermal efficiency as we define for geothermal wells, it is the work output divided by the energy input, right? So the energy input that we have here is more of like the exergy. It's sort of how much is the potential for the hot geothermal water to do work, right? So it is as we saw in the formula before, energy input is mass flow rate at state 1, or mass flow rate of the geothermal water that we're extracting, times its enthalpy at state 1 minus enthalpy at a standard or a reference state. What is this reference state? 25 degrees Celsius and 1 atmospheric pressure. So as we know, we are sort of treating this as a saturated liquid. So all we need to know is what is, let's say, HF at 25 degrees Celsius, and that will be the H naught for all calculations that we do, right? So simply when we put these numbers in, what we get as E naught in is 71,743 kilowatt. So yeah, the efficiency is rather small, 6.84%. Okay. Now, this is again typical of geothermal power plants. Remember, we're dealing with reasonably low temperatures. 200 degrees Celsius is a very low temperature. And by the way, we are not making use of this directly. What we are making use of is steam at 151.8 degrees Celsius. Not very hot steam. So obviously, the temperatures are on the lower side. Sorry, the efficiency is on the lower side. Now, and yep, the calculation for EN is sort of given here. So this 104.83 is a number that you will see very often because, as I explained, it's simply HF at standard temperature, not a strong functional pressure. So we'll just be using that throughout for any calculation of geothermal power cycles. Now, moving on, the third part of this question is, all right, we are having reasonably hot water, and we sort of sending it back, right, in a single flash power plant. So let's assume the single flash power plant is retrofitted to operate as a double flash plant, which kind of makes sense just from the resource utilization perspective, right? Economics, we don't know, but for as far as the overall utilization is concerned, well, yes, it may make sense because we don't want to reinject really hot water back into the ground. So here it says that the first and the second flash pressures are selected as 500 kilopascal and 150 kilopascal. So this is the first flash pressure as we just solved, and the second flash pressure is 150 kilopascal. As expected, it should be lower, right? So you have liquid and vapor. The vapor goes up and expands within the turbine. The liquid goes here. It's flashed again, and P6 is 500 kilopascal. but P7 is 150 kilopascal, right? A lower pressure. Now here, once it's flashed, we have again a saturated liquid vapor mixture. So this is vapor, and this part here is liquid. Liquid, you can re-inject it back into the well. Vapor, you can send it. Now here, there's a mistake in this infographic, in this sketch or the schematic here. This is at a lower pressure, 150 kilopascal. So it has to expand in a different turbine, right? In a different low pressure turbine. So you'll have a low pressure turbine and a high pressure turbine. We can have the output of both turbines going through a similar condenser. That's sort of okay, as long as the output pressures are the same. But yeah, it has to be two separate turbines, right? In reality, not like the way it's shown here. So either way, what we want to do is to calculate the power output and thermal efficiency of this double flash power plant. Everything else remains the same. So essentially, what we're looking for is to simply calculate how much is this power output that we can get from this other low pressure uh, steam turbine, right? And then what is the efficiency? Okay, so all we need is we need information on basically state 8 and state 7. We want the quality at state 7 so that we can understand what is the mass flow rate of the steam that goes in there. And yeah, we just need some conditions in there. So from the question, we know the pressure P7 is given. P7 is given as 150 kilopascal. We know that the flashing process is isenthalpic. So H7 is equal to H6, and we have H6 from the previous parts. So we have H7 already. So using these two properties, we can find out the other properties of interest. Now, the temperature at T8 is going to be the same as T7. So T7 is T8 is equal to T9. All of these are saturated, is just saturated mixture. T8, state 8 is simply saturated vapor, and and state 9 is liquid, but all of them are exactly at the same temperature at different enthalpies though, because of the different states, right? So temperature at state 8 is 111.35 degrees Celsius. Now enthalpy at state 9, which is liquid, is HF at 150 kilopascal, so that's 467.13. H8 is saturated vapor, so it's Hg at 150, so it's 2693.1 kilojoule per kilogram. Now, just like what we did previously, we need to find the quality, right? Quality at state 7. So how do we find the quality at state 7? We use the exact same method, right? So at state 7, after flashing, what we have is a mixture of liquid and vapor. And so you find its enthalpy as HF plus X7 times Hg minus HF, right? So we have HF here, we have Hg here, and H7 is something that we already know because H7 is equal to H6. So the only unknown is X7, the quality at state 7, and we can rewrite the equation that I just wrote here in this form and then plug in the numbers to get the quality. So the quality here is much smaller. It's 7.77%, right? So 7.77% of the of the hot liquid that came in here is converted to vapor by flashing. So that's what goes up here. The remaining, about 92 point something percent, 92.3% is still liquid and goes back, right? So now for finding out the power output of the second low pressure turbine, what we need is the mass flow rate at state 8, right? So this is state 8 here. So the mass flow rate at state 8 is simply X7 times the mass flow rate at state 7, right? So when you plug in the numbers, 6.988 kilogram per second is what comes out. So this is how much we are extracting more for the second low pressure turbine, right? And so the work output in the low pressure turbine would simply be m dot 8 times H8 minus H4, right? Because we're saying that the exit of this low pressure turbine is also the same as the exit of the high pressure turbine that we had before, right? And in the first flash that we considered. So we have all the numbers. We have H8, we have H4. We just calculated m dot 8. So plugging in all the numbers, we can get 3.026 megawatt or 3026 kilowatt. Reasonably large power, something that you don't want to give away for free, right? As long as the economics work out. So now we have the work output. The total work output will be simply sum of this and the work output from the previous case. So the thermal efficiency of the plant would now be 4,909 kilowatt, which we had from the high pressure steam turbine, plus 3,026 kilowatt, which we have from the low pressure steam turbine, divided by the energy input, right? With this, what has remained the same? Nothing has changed. We're still extracting the same quantity of geothermal water, and you can see that the efficiency has gone up to 11.1%. So, as discussed before, this is obviously a better utilization of the hot resource, of the hot geothermal resource. And well, again, even now, you can see that the water that we are sending from this second separator, still hot water, is 111.35 degrees Celsius. Um, and it could still be used for heating purposes. The only problem with geothermal resources is the fact that they are usually located in very remote areas, so you don't really have a customer who needs heating, right? So, which is essentially why we use them for extracting power. So power, once you generate electricity, you can simply send it anywhere. You can do that with hot water. So when there is an economic case to be made, well, it makes sense to actually not re-inject this state 9 into the well, but to actually extract hot water and then send it back. Okay, so this is uh, uh, a rather simple example to give a good overview of what kind of numbers we are dealing with and how we can extract energy from a typical geothermal power plant. And again, I covered flash simply because majority of the resources that we have around the globe, these are liquid dominated sources. So you don't really have dry steam at majority of the resources. So this is one of the most commonly used way of extracting power from a typical geothermal resource. Okay, now let's move on, and now let's talk about a binary cycle and a binary geothermal cogeneration plant. So cogeneration again simply means you're generating electricity plus heat. Okay, so let's see what's happening here. So here we have a binary geothermal cogeneration plant, which is using geothermal water at 165 degrees Celsius. Okay, so that's the geothermal water that's coming in at state 5. And with isobutene as the working fluid. So isobutene is the working fluid in the binary cycle, right? It's the working fluid in the cycle that we have here. Okay. So the mass flow rate of geothermal water is given as 175 kilogram per second. So that's again the mass flow rate at state 5, 175 kilogram per second. The work output is 6.9 megawatt. So that's the work output, the net work output from the binary cycle. And as we discussed before, it basically is turbine work output minus the fan work input for the condenser. It's usually an input condenser. Now, here it says that it is determined that the geothermal water, it leaves the plant at 85 degrees Celsius. So state 6, it's 85 degrees Celsius. Okay, reasonably hot. You don't really want to lose this hot resource, right? So here, what we are doing is instead of dumping it, this rather hot water, reasonably hot water, reinjecting it back into the ground, we are sending it through another heater. Okay, so this geothermal water leaves the plant at 85 degrees Celsius and then leaves the heater at 65 degrees Celsius. So it goes through a heater to heat up water and it leaves the heater at 65 degrees Celsius. Okay, so that's state 7. Now the fresh liquid water, which is actually going through this heater and getting heated by this 85 degrees Celsius water, is actually heated to 75 degrees Celsius. So that's state 9. Okay, and it is used for space heating, and it goes through various homes or office space, whatever, and then comes back and enters this heater again for getting heated at 50 degrees Celsius. Okay, so all this information is given to us. Okay, now what we need to determine is a few things. First, we need to determine what is the rate of space heating what is provided by the system and the mass flow rate of water what is used for space heating. Now, in reality, we need to find out how much is the heat that is getting transferred from this geothermal water. Now, for the purpose of this question, we are not provided with any heat loss to the surroundings, right? So we assume all the heat transfer that's happening from geothermal fluid is getting transferred to this fresh liquid water. So all we need is simply to calculate the change to calculate the heat transfer from this hot geothermal liquid, which is m dot Cp delta T, and we are taking m dot Cp delta T, not delta H. Well, which is also an option, simply because here the water is not undergoing any phase change, right? It's liquid water at state 6, it's liquid water at state 7. So easy way is, just make use of Cp delta T to calculate change in enthalpy. So delta H is basically Cp delta T, or it's a good approximation, Cp delta T. Now Cp again, if you want to be more accurate, you can get it at the average temperature of 85 and 65 degrees Celsius, right? So um, which would be 75, or you could simply, take 4.18 kilojoule per kilogram degree Celsius. Both options are okay. So m dot Cp, this is the delta T for the geothermal water. So this is the amount of heat that is getting transferred from geothermal water to the fresh water. Okay, so 14,630 kilowatt. Now that's the first part done, rate of space heating. Now what is the mass flow rate of water? Well, again, this simply requires energy balance for the heat exchanger. Okay, so we simply have to equate the heat lost from geothermal water to the heat gained by the cold water. So this heat lost by the geothermal water is exactly equal to the heat gained by the fresh water. So this again is equal to mass flow rate of fresh water times Cp, the same value, right? Times delta T. Now delta T here is smaller. Uh, uh, Sorry, yeah, it's the exact same delta T, that it's slightly larger. Sorry, it's not smaller, it's larger. It goes from 50 to 75 degrees Celsius. So delta T is larger, so m dot W is going to be smaller. Okay, so when you do the math, the m dot W, or the mass flow rate of this water, comes out to be 140 kilogram per second. So this is the mass flow rate of fresh water. As delta T is larger, it's getting heated by 25 degrees Celsius. So obviously the other fluid, the other geothermal water will have a larger mass flow rate. So this is perfectly fine. This is what makes sense. So we have solved both parts of it. Now let's look at the second part. So here we need to determine the thermal efficiency of the plant and the utilization factor of the entire geothermal of the entire cogeneration plant. So first, when you talk about the efficiency of the plant, well, it's simply the network output divided by the energy available in the geothermal resource, right? So the that's essentially one way of looking at the thermal efficiency. Okay, so when we discuss about the binary cycle, we said another way to look at it is to simply find out what is the network output from the turbine and the minus the work input for the fan for the condenser, divided by what is the heat that is transferred to this binary fluid, right? So this is a special case for binary fluids. And so here what we'll find out is how much is the heat transferred to the binary fluids, which is, well, mCp delta T again. So the delta T that we're talking about is from T5 to T6, right? So we have the mass flow rate, same mass flow rate, same Cp for water, and this is the delta T that's happening in here. So this is the amount of heat transferred to the binary fluid. Now, out of the 58,520 kilowatt transferred, 6,900 kilowatt is what is the net power output. So the thermal efficiency is simply 6,900 divided by the heat input, comes out to be 11.8%. Okay. Now, this is the thermal efficiency of the power plant. You can also define it as work output by EN. This is also another way to compare it with other geothermal cycles. Here, the work output would remain same. The energy in would simply be different. It'll be m dot times h5 minus h naught. Okay, so this will give you a slightly lower value of thermal efficiency, but both are okay. And the question would very clearly specify which one I'm looking for. Now, the second part is the utilization factor for the entire cogeneration plant. So now when we talk about the utilization factor, we could have actually reinjected this hot water at state 6 directly into the well, but we are not doing that. We are still making use of the thermal energy available to heat up the fresh water, right? So we have increased the utilization factor. So we're not just producing power, but also we're meeting some of the space heating needs. So the utilization factor of the power plant would be the work output that we have from the power plant plus the heat that's being provided divided by the heat input. Now, remember the additional heating that we are providing here it's sort of a bonus, right? It's from sort of waste heat, so we don't really take that into calculation when we are doing the utilization factor. Again, this is one way of doing it. You could also, if you want, take that into account, take the total heat input into account. But in this way, the utilization factor would be 6,900 plus the heating that we calculated divided by the same number, right? 58,520, what is the heat transfer to the binary cycle. And here the utilization factor comes out to be pretty large. I mean, along expected line, it's you're providing power plus heating, and heating is a reasonably large number. So just to say that, wherever economically possible and feasible, uh, it makes sense to sort of make use of geothermal resources for meeting the space heating needs. All right, so these are the two problems, and we'll conclude the chapter by just saying that although this chapter has focused mainly on different ways of using geothermal resource to extract power or to generate electricity, right? There are other ways in which you can use. Okay, so one is district heating, as used in Iceland, as we discussed before, but you could also use it for flower growing, as it's used in Canada, for drying of tomatoes, as done in Greece, or for aquaculture, where you just heat hot water. So you can use the thermal energy available in the hot geothermal water for many different purposes. And electricity is one, of course, one option that makes sense when you have medium to high enthalpy resources. But if you have low enthalpy resources, which is what we have in the majority of places around the globe, there are other options that still can be used to offset the energy from, let's say, burning some fuel or uh, from electricity, right? So to offset the energy that's needed for drying tomatoes, for growing flowers, for aquaculture, instead of getting this heat by using an electric heater or by burning some fuel, you can use geothermal energy to make use of it. So many options available, but of course, electricity generation is one of the most uh, let's say common, or one thing that makes sense, simply because as I said before, geothermal resources are located typically at remote locations. So if you don't have any application nearby, electricity generation is what makes sense, right? So with that, we'll end this chapter.